Okay, let's make a start. So you should all have a handout today, which you're going to need because you're going to be adding lines and things to it in a short while. So welcome to the penultimate lecture. Just one more to go. And today we're getting on to the final query that I put up right at the beginning when I said, why do we need a better theory than curly arrows? And the example that I gave you was, we now know that the Diels-Alder reaction is a good reaction. But the question is, why, when you add some substituents to this, does it suddenly go 10 to the 10 times faster? So this thing, 800 atmospheres, 120 degrees C, 24 hours. This thing, you mix them, and the product just separates out. So that's really what we're going to be looking at initially, how you can look at the rates of reaction. So we're no longer talking about allowed and disallowed. We're talking about how fast. The second thing we're going to tackle is that of regiochemistry. Because when these two things with substituents on them react, they could form the product with the two compounds close together or with the compounds far apart. In fact, you only get this one. So the question is why? And then the final thing we're going to tackle, but not until tomorrow's lecture, is these two substituents could be formed cis or trans. In fact, you get very high selectivity for the less stable form when they're cis. How can we explain that? So those are three of the things that we need to get through today. So we're going to start with that first one, the rates of reaction. And the absolutely key thing to remember about the rates of reaction is, again, something I mentioned in the very first lecture when I talked about why are front two orbitals the important ones. And that is that the extent of stabilization of a transition state, the extent of interaction between two things coming to react together, is critically dependent on how far apart in energy the two orbitals are that are going to overlap. So when we're looking at rates, you can imagine two situations. Again, this is back from the first lecture when I had my A and my B, and if the energy level of the HOMO of B and the LUMO of A, if they have very different energies, if they're a long way apart, they can't interact particularly strongly. So that as they mix, as you go into the transition state, you get a relatively small gain in energy. On the other hand, if those two things are very close together, so maybe that's my LUMO and that's my HOMO, if they're close together in energy, they tend to mix very efficiently. And you maybe get a picture that looks more like that. Big drop in energy as they overlap in the transition state. So therefore this will be the fast reaction, and this will be the slow one. And that's the fundamental way that you use front two orbitals, the energies of front two orbitals, to decide how fast reactions go. And this is not restricted to pericyclic reactions. It applies to pretty much all reactions that you'll come across in organic chemistry. Now if we take the specific example we're going to look at, which is the Diels-Alder reaction, and we've got a diene and we've got an alkene component. So here's our diene, and here are 4 energy levels of that diene. Okay, so here I have the HOMO and the LUMO. Let's consider it reacting with ethylene. And what are the orbitals of ethylene going to look like? Well, they're actually going to be, roughly speaking, there and about here. Now you might ask, why does ethylene have a higher LUMO and a lower HOMO than butadiene? Well, one way you can think about it is if you imagine making butadiene by bringing two molecules of ethylene together and mixing the orbitals. So if you imagine you started off with, say, 2 of these, when they mix together to form the butadiene, and one's going to go up, one's going to go down. So inevitably, butadiene is going to have a higher HOMO than ethylene. And by the same argument, it's going to have a lower LUMO. Okay? So now when we're looking at the interactions, you've got that one there, or this one here. They're about the same size, and neither of them is particularly close in energy. So it's going to be a relatively slow reaction. Now, supposing we have a situation where our alkene, instead of being ethylene, is acrolein. Okay, it's the molecule on the example. So acrolein is that molecule. Now, a little bit later, we're going to go into how you can actually work out the trends in energies. But for the moment, just think about it as a chemist. Okay, acrolein, you know, is an electron acceptor. It's a Michael acceptor. You want to do conjugate additions to it. Okay, therefore, it must have a low LUMO. That's what makes it an electrophile. And it turns out that the HOMO also goes down in energy. So if we look at the orbitals of that, then the LUMO has got to be lower in energy, and so is the HOMO. So it will look more like that. Now I'm just going to just dot across here so we can see our levels. Okay. So now if we think of the energy interactions, okay, this one between the HOMO of ethylene and the LUMO of the acroleins, they've got closer together in energy. So that's going to be a faster reaction. Whereas the other one, here, that's now going to become a very small interaction indeed. They're even further apart in energy. So therefore you can conclude that acrolein is going to react faster with butadiene because there's a strong interaction between the HOMO of butadiene and the LUMO of acrolein. And effectively what that's telling you is that there's a charge transfer in the transition state. Some of the electrons from the butadiene are being transferred into the very electrophilic acrolein as you go to the transition state. And that charge transfer gives you back some energy. Supposing we used a very electron-rich alkene, what would we find then? So an example of a nucleophilic alkene would be a vinyl ether. So that's ethyl vinyl ether. Well, that's very nucleophilic, okay, because it's very like an enolate, in fact, not as powerful, but it's like an enolate. You've got the oxygen lone pair donating electron density into the pi system. So it's nucleophilic. Something that's nucleophilic must have a high HOMO. That's what being a nucleophile means. So this is going to have a high HOMO. And as it turns out, it also has a very high LUMO. So now if we consider what's going to happen to the energies, now we've got a very strong interaction between the HOMO of the ethyl vinyl ether and the LUMO of the diene. And a very weak interaction the other way around. Okay. So the conclusion from that will be that, in fact, you'd expect the reaction to be fast with both very electron-poor systems and very electron-rich systems. In one case, it's fast because you get good transfer from the diene to the alkene. And in the other case, it's because you get a charge transfer from the alkene to the diene. Okay. But overall, that's how you consider the rates of not just Diels-Alder reactions, but to be honest, pretty much all reactions. Okay. So what we're now going to do is we're actually going to look at some sort of more real examples, because as you'll see, that's a nice ideal example, but in practice you don't actually tend to find it very often. The reason being that dienes are actually rather electron rich anyway. So you want the first page of your handout. Okay. So this is actually what the energies really look like for butadiene. Okay? As I said, butadiene is actually quite an electron-rich species. So in fact, the energy levels are quite high anyway. And what you find with, here's your things we looked at. So here's the acrolein, very low energies. Cyclohexene, typical in the middle. And ethyl vinyl ether, high energy. So when you look at the energies for these, then you can see that, in fact, in all cases, they're actually dominated by the interaction between the diene HOMO and the alkene LUMO. So even in the case of the electron-rich species, the smallest energy gap is still between the HOMO of the butadiene and the LUMO of the ethyl vinyl ether. Okay, so it's always the red lines which are going to dominate. They're always closer than the blue lines. Okay. So the prediction for the rates is going to be, here we have a very small gap. Okay, as you'd expect, electron-rich diene, electron-poor alkene, so you get a very fast rate. If we move on to here we now have an electronically neutral alkene and a much bigger gap, so a smaller rate. And then finally we go to the electron-rich alkene, biggest gap of all and the smallest. And this is what you see for normal Diels-Alder reactions. You actually see that the more electron-rich the alkene is, the slower the reaction goes. Okay. Suppose we use a different diene. Now in this case, we're using this acridine as our diene. Okay, and in fact we're using this middle diene component here, that double bond and this double bond to the nitrogen. Now if you look at that, you can see that's actually a very electron-poor system. Okay, it's got an N plus in it. So in this case, the its HOMO and LUMO are very low in energy. So now what are we going to find when we look at the interaction with the same three alkenes? Okay. Well, if you go for acrolein, in this case, there's actually not much to choose between the two different ways of transferring the electrons, but in fact both of them are very weak. Okay, it's a big gap in both cases. Whereas if you go to cyclohexene, then you find that you get an electron donation from the cyclohexene to the diene, and then you go to ethyl vinyl ether, and it's an even bigger interaction because we're even closer in energy. So again, when you look at the rates that that's going to correspond to, the slowest now, which used to be the fastest, the slowest is going to be acrolein, then cyclohexene, and then finally ethyl vinyl ether is going to be very, very fast. So this is known as a Diels-Alder with inverse electron demand. Okay, so in most Diels-Alder reactions, there's a net electron transfer from the diene to the alkene in the transition state. In this case, it's the other way round, and you get the reverse order of reactivity of your alkenes. But you'll notice that in both cases, simple cyclohexene is pretty unreactive. It's in the middle. Finally, we have classes of reactions where the HOMO and the LUMO of the diene component are actually quite close together. And that's particularly common in 1,3 dipoles. So phenyl azide, which is drawn out here, okay, is a typical 1,3 dipole. It does the 1,3 dipolar cycloadditions that you saw in about lecture 3. In this case, when it's interacting with acrolein, then it's dominated by electron transfer from the 1,3 dipole to acrolein. So there's your interaction. By the time you get to cyclohexene, there's not a lot in it, but actually it's more dominated by transfer from the cyclohexene to the 1,3 dipole, and then go to an electron-rich system, and that becomes even stronger. Okay. So when you look at those, you now get the sort of U-shaped curve that I almost said you would on that when I was talking on the board. So acrolein is fast because it can accept electrons from the 1,3 dipole. Ethyl vinyl ether is fast because it can give electrons to the 1,3 dipole. And cyclohexene is stuck there in the middle, not as fast as either. Okay. So that's rates of reaction in Diels-Alder reactions. We now need to look at both. I've been making these statements about the energy levels of the orbitals, and we're going to need to know something about relative orbital sizes for tackling regiochemistry issues. So the question is, how can we actually work these out? So to actually work out what these energy levels should look like, and as you're going to see, actually the relative sizes of lobes in orbitals, we use something called the peturbation method. It's something you might have come across in physical chemistry if they talk about solving the Schrödinger equation. Because there's a rule that effectively says that if you perturb the Schrödinger equation, you can always find a lower energy form of it. And that's effectively what we're going to use, but we're not going to use equations because we're organic chemists, we're going to use pictures. So if, for example, I take the case of acrolein, okay? And I want to model what acrolein is going to look like, what the orbitals are going to look like, what the energies are going to look like, but I want to do it on the back of an envelope because I'm an organic chemist. I don't want to have to roll out my computer. How can I do it? Well, you think, well, what is that? Well, it's an electron withdrawing group. What is the ultimate electron withdrawing group? Well, it's a carbocation. Okay? So I can model this as being a mixture between ethylene itself, the unperturbed system, plus I'm going to mix in a little bit of ethylene with a plus charge on it. Okay? So what I'm saying is, this is, if you like, the ultimate electron withdrawing group. Here hasn't got any. This is going to be somewhere between the two. So I can approximate what the orbitals of this is going to look like by mixing the orbitals of that with some of the orbitals of this. I'll talk about energies in a moment, but first of all, let's look at the sizes of orbitals, because that's actually going to be what's critical when it comes to determining regiochemistry. So if I want to find out what the LUMO of acrolein is going to look like, and it's going to be the LUMO that we want, after all, it's an electron deficient species. The LUMO of acrolein is going to look like the LUMO of ethylene, okay, which is that one, plus I'm going to mix in the LUMO of an allyl cation. So what's the LUMO of the allyl cation? Well, it's the second orbital up, okay, got a single node. It looks like that. Okay. So when I mix these together to get the orbital of this, I'm going to get something which looks like that, okay, with a large lobe on the terminal position and a much smaller lobe on this position. Okay. Now, just one thing to notice there. You'll notice that I conveniently chose to shade both of those. You might say, well, hang on, if you'd chosen not to shade that, you should subtract them and it'll get weaker. Okay, well, in fact, I really should be adding electron densities at this point. Okay, and electron densities are the squares of the orbitals. Okay, so they're all the same phase. But I'm not going to do that because you get terribly confused, because suddenly I'll be drawing a LUMO with both phases the same colour. So what I do is I stick to the orbitals you're all familiar with, okay? But just remember that you can't subtract them, okay? Because it's really the electron densities you're talking about. And the way of doing that is just always choose to make sure these are the same phase. Okay, you'll never face a situation where it causes a problem. Yes, this does appear to get smaller compared to that. And that's because you've only got 2 electrons. Okay, so if you make one of them bigger, the other one's got to get smaller. because you've only got 2 electrons in total. Okay. So there's a prediction for the LUMO of acrolein. It's going to have a large lobe at the end and a small lobe there. What about the energies of that system? Well, here's my ethylene. And here's my Lr cation. Okay, so that's the unperturbed system. That's the extreme system. And look what happens to the HOMOs and the LUMOs. Okay, that goes to there, and that goes to there. Now, acrolein is going to be somewhere between them. Okay, we don't know where, and we don't really care. It's going to be somewhere, maybe there, and there's our acrolein. Okay, because the one thing we can be certain of is that compared with ethylene, acrolein is going to have a lower HOMO and a lower LUMO. Yeah, you know, it might be further towards the cation, it might be not so far. But in all cases, the trend is going to be correct. So when I was talking about acrolein having a low HOMO and LUMO, this is how you can prove it. This may sound rather hand-wavy and drawing pictures. In fact, mathematically, it's completely rigorous. But I think we prefer the pictures version of it. Okay, that's acrolein. I should say what I'm going to do is I'm just going to go through this peturbation method in 2 examples, which are actually going to allow us to answer that regiochemistry problem on the first slide. I'm then going to come back to them and actually go through rather more examples on the PowerPoint. But I'm doing the slow version first. So the other bit that I needed to do my... I wish I could save that, but I must write it up again later. Because I've only got one board here. So the other thing that I need for that problem that I gave in the first one is I need to know what the orbitals of that species are. Okay, that was the dying component. Okay, and again I'm going to treat it as a perturbation method where, well, you think, well, what is that oxygen doing? Well, it's an electron donating group. Okay, what's the ultimate electron donating group? A full-blown carbanion. And of course, I'm picking things that I can draw the orbitals of, because I can draw the orbitals of any N alkyl chain with any number of electrons in it. So I'm going to approximate that as being butadiene plus, you mix in, the pentadienyl cation, some amount thereof. Now, it's a diene, it's electron rich, so I really want to know about the HOMO. The question is, what is the HOMO of that system? Well, the HOMO of butadiene is the second orbital up, so it's the one with the single node. So that's the HOMO of butadiene. What is the HOMO of the pentadienyl anion? Well, it's got 6 electrons, therefore the highest occupied is going to be the third orbital up, which is the one with 2 nodes. As it turns out, the nodes are actually there and there, so the orbitals of that look like that. That's the HOMO of the pentadienyl cation. So I mix them together, and the prediction for the HOMO of this, you can see that this atom is getting reinforced by these 2 adding together, whereas this termini is not having anything added to it at all. There's a node in that position. We don't really care what happens to these 2 positions because they're not, if you like, where you're forming the new bonds. So my prediction is that that's going to be large and that's going to be small. If you want to, you can put these 2 orbitals in as well. but really we're only concerned with the ends. What about the orbital energies of the methoxydiene? Well, here I have to have butadiene, that's butadiene with its two filled orbitals. And then I have a pentadienyl anion, and that actually has, it looks something like, not really terribly to scale, but the middle pair of electrons is more or less non-bonding, it's more or less in the middle. So this is the pentadienyl anion, okay, 6 electrons, fill the bottom 3. And again, you look at the mixing, and so I should have made that a bit higher to make it a bit more obvious. But you can see that your methoxy substituted diene is going to be somewhere in here. So maybe it's here. Okay. But the prediction is clear. Okay. The HOMO and the LUMO must both have gone up in energy relative to the unperturbed diene. So that's why we say it's an electron-rich system, particularly because the HOMO energy is higher. It happens the LUMO energy is higher as well. Now, finally, we come to solving the problem that we had right at the beginning. I'm going to leave that up, and I'm going to bring back acrolein. Now, we know that we want the LUMO of acrolein. We've already seen that. And the LUMO of acrolein had a large lobe there and a small lobe there. And now we come to the simple method, really. How do you decide the regiochemistry? You simply overlap the biggest lobes of the two components. It's as easy as that. So in this case, that's the biggest lobe on there, that's the biggest lobe on there, so that must be the regiochemistry of formation. Okay? And obviously your other bond has to form there. I should say, when I say you pick the largest lobes, it has to be consistent with your curly arrow mechanism and your allowed process. So therefore you get, as your product, the so-called ortho product, where your two substituents are close to each other. Okay. So that essentially is the method. Work out the orbitals on your two components, overlap the biggest one, and it will very, very reliably predict the regiochemistry of your cycloaddition, or indeed of many other reactions. Okay. So that really is the key point. Everyone's got that? Okay. So we're now back onto the handouts. Okay? And effectively what I'm going to be doing is just going through the different types of alkenes and dienes that we can get, and just showing you how you deal with them using the perturbation theory, what the orbitals look like. But to be honest, you've seen almost all the method already. The only thing I haven't shown you yet is how to deal with extended conjugation, but we'll come to that in a moment. Okay. So we're using perturbation to predict them. And so electron withdrawing groups, okay, we're treating as a C plus perturbation. Okay, so we had acrolein, but you can think of lots of other things which are electron withdrawing groups. Things like esters, cyanides, anything like that. electron donating groups, such as O-methoxy, and critically, alkyl groups. Okay, now this is not obvious, okay, because after all, a methyl group doesn't have a lone pair. But if you remember when you were talking about particularly stability of carbocations, okay, a methyl group acts as an electron donating group. Okay, think about toluene. Toluene is an orthopara director. Okay, we discussed it in terms of what was called hyperconjugation in the second year. So alkyl groups are electron donating groups. Of course, they're nothing like as good as having an O-methoxy. They're very weak. But that's the whole point of perturbation theory. It doesn't matter how far along the scale you are when you're only interested in the trend. Okay? And the one we haven't seen yet is how do you deal with extended conjugations, so styrene, for example. Well, again, what we do is we take the simplest possible form of extended conjugation, which is a vinyl group, and we use that as the perturbation. You'll see how that works a bit later. Okay. So here is a case, actually it's not one you've seen, but we're dealing with an O-methoxy, we're dealing with an electron donating group as our perturbation. Now, you saw that with the diene because I wanted to show you the Diels-Alder reaction, but it could also be for the alkene component. Remember, we talked about ethyl vinyl ether quite a lot when we were talking about energies. So again, the perturbation is ethylene plus delta bit with a carbanion on it. So again, when you look at the prediction for the energies, here's your allyl anion, here's your ethylene, so the energies have to go up. That tells you that both propene and the methoxy, methyl vinyl ether, are both going to be more electron rich, have higher energy orbitals than ethylene. In terms of the predictions of the orbital sizes, then the HOMO, which to be honest is what you're going to be bothered about, is going to be the HOMO of ethylene plus the HOMO of the allyl anion. The HOMO of the allyl anion is, again, the second orbital up, single node, looks like that. So it predicts that the larger lobe is on this position. This sort of fits with your experience, because if I showed you, if this was an O-methoxy or even a methyl group, you say, well, where's it going to protonate? Okay, hopefully all of you would say, well, it's going to protonate on the end to leave the carbocation in that position. Well, you would have explained it by saying, well, the carbocation is more stable in that position. But in fact, another way of explaining it, which in fact is more accurate in many cases, is actually to say, well, in fact, the coefficient of the HOMO is bigger on the end, and therefore that's where the proton's going to go. Okay? We could look at the LUMO, but no real point, because you never really want to use the LUMO of vinyl ether, but you could do it in exactly the same way. This is the one that you saw, so I'm not going to go through it again. So this is the substituted diene, so we've seen that. But this one is worth talking about, okay, and all these are on your handouts. So what happens if your substituent is on the 2 position of a diene? Okay, well, the method is fairly clear. You're perturbing it with this system, where you've replaced your X group with a carbanion. The important thing, though, if you think about that anion, think where you could put it mesomerically. You can donate it into here, but actually there's no way of getting that anion up here. So in fact, a substituent in this position has no real effect on this alkene up here. Okay? So when you mix it in, you're just mixing with the allyl anion. And therefore the prediction is going to be that it will get bigger on the end here and not really affect that end very much at all. Okay. This is the example that we did. The Z substituted, the electron withdrawing group substituted system, where we modelled it as a carbocation. And this is how we did it again, so you've already seen this. And I'm just going to point out that if you wanted to do it with a diene, then you would follow exactly the same method. So you'd use a pentadiene cation as your thing you mix in, and you'd end up working out that these were what the 2 diene systems would look like. You are expected to be able to work this out. Okay, you've been shown the method, and you just apply the method to any of them. I mean, if you want to, you can learn them more, but a bit of a waste of time. Far better just to know the method, particularly because the exam questions will usually ask you to explain why you think the orbital's that way around. And then finally we come to the example that you haven't seen yet. and that is how to deal with extended conjugation. So if you've got, well, in fact, you could almost, I mean, C typically would be a phenyl group, but it could also be an alkene or a triene or anything with extended conjugation. What effect do you have? And like I said, the only thing we can really do is to model it as being the one thing that we can work out the orbitals for, and that is a simple ethylene group. So this has extended the conjugation of the alkene. If you look at the energies, you've already seen that the energy of butadiene, the orbitals look like this, where these two, the HOMO and the LUMO, are closer together than they were in ethylene. So remember the argument about two ethylene molecules coming together to form butadiene. And so in this case, it's a bit different to the others. The prediction is that the HOMO will get higher, but the LUMO will get lower. So they get closer together. In terms of the orbital sizes, then, so we want to, what happens when you extend conjugation on ethylene? Here's ethylene, you mix in butadiene HOMO, so you can see that that is going to be bigger than this. Now, at this point, we have to do something rather different, because so far, we haven't really worried about the sizes of orbitals when we draw the orbitals of, say, butadiene or pentadiene, things like that. Now, for the first time, we do have to care. Now, fortunately, the method that I showed you right at the beginning for working out the phases of orbitals actually turns out to be pretty accurate for working out the sizes of orbitals as well. Effectively, because you're just looking at particle in a box. It's perfectly rigorous. Okay. So if you look at the HOMO of butadiene, remember the node is here, then you can see that this carbon is a lot closer to a node than that carbon is. Okay? Therefore, the orbital on this atom is going to be rather bigger than the orbital on that atom. So you simply have to be able to draw your sine wave with tolerable accuracy, and you can predict which is going to be the bigger orbital. Okay, so in this case it's the one on the end. So I've drawn this with that large and that small. Okay, mix them in, and the prediction is that for any extended conjugation, the end is going to be bigger than the internal one. And again, this is consistent with what you know about the reactivity of things like styrene. If you took styrene and you protonated it, you would expect it to protonate on the end to leave the carbocation next to your phenyl group, because benzyl cations are stabilized by deconjugation, by delocalization. Okay? Here's another way of arguing it. In fact, it's that end lobe which has the highest coefficient on the HOMO, so that's what's going to protonate. In this case, you actually do need to know the LUMO as well, because as the HOMO and the LUMO have got closer together, you're actually more likely to need to use either when you're looking at a reaction. And so the LUMO of the extended conjugation, you just have to take the LUMO of butadiene, and again that's this one. And again, if you look at it, if you look at where that node is, it's actually only 1/3, 2/3, so it's closer to this position, and therefore this is going to have the greater coefficient. Hence the end is going to be larger than there. Final point really about the extended conjugation. Okay, in the cases of the electron withdrawing or the electron donating groups, we modelled them as the extreme form. So the most powerful electron withdrawing you could have as a cation, most active electron donating group was a carbanion. So any other system is going to be somewhere between the two, and quite frankly probably a lot closer to your unperturbed system than to the perturbed system. But with these, that doesn't apply. Okay? In fact, you could be more conjugating than a simple vinyl group. Okay? So here, when you're looking at things, although it may look as if the energy differences are rather, the size differences are rather smaller here from here, but you're likely to have to mix in all of them, or even more than all of them, to predict what your molecule is going to look like. So although it looks like a smaller difference, it actually is more significant. And again, if I go back to the energies, you know, although I've put this here, in fact, it could actually be over here somewhere. Yeah, it could be that the HOMO-LUMO gap is even smaller than butadiene because I've extended the conjugation even further. The important thing is that the comparison of ethylene and butadiene gives you the trends. It tells you roughly what happens. Okay. And again, I'm not going to actually show you how to do them. You've seen the method, but this is what it should look like when you work out the orbital sizes. And my suggestion is just try one or two of them yourself and check that you get the same answer. And if you do, you'll be able to do it for all the others. And the final thing that I want to look at today is, what do you do when you've got several substituents on your diene or your alkene? Okay, so supposing we have this situation down here where my diene has got a methoxy group on, but it's also got two methyl groups, and my alkene has got not only got an ester group on it, it's also got a methoxy group and an alkyl group. How do you deal with it? Well, fortunately, it's very simple. You just pick the most important and forget all the others. It's the same reason that when you're looking at orbital overlaps, you just bother about the biggest orbital overlap. You don't bother about the others, because they always tend to be dominated by one effect. So which is going to be the most important? Well, it turns out that electron withdrawing groups, where the electron withdrawal is a mesomeric effect, are the most powerful groups. So by mesomeric effect, I mean by conjugation to a carbonyl, or maybe to a sulfoxide or a cyanide or a nitro group. Okay? These are the most powerful effects. Next most powerful are electron donating groups, where there's a proper lone pair there donating in mesomerically. So ethers, thioethers, amines. Okay, where the lone pair is directly feeding into the pi system. The next most potent tend to be the extended conjugation systems, though I have to say it gets a bit woolly here. It depends just how conjugated and do you have any other substituents. You may be sure that on the exam you won't be given any really fine things to distinguish between. It'll tend to be one of these and one of those. Okay. Here it does get a bit more harder to tell, but generally speaking the things with an extended conjugation are more potent than electron withdrawing groups where it's an inductive effect. Okay, so none of these systems interact directly with the pi system. They're all inductive. So here it's an oxygen, but it's an extra carbon further away. So its only effect is inductive through the sigma bond. CF3 group is actually quite a potent electron withdrawer, but again it's only through the sigma framework. And likewise an ester, not in conjugation. Okay, and then finally it's simple alkyl groups, which are just about electron donating. So if I look at this example, in this case, I simply ignore my two methyl groups. Okay, it's going to be totally dominated by the methoxy. In this case, it's going to be totally dominated by the ester, and I will simply ignore the effect of the methoxy and the methyl group. Okay? So when you see one of these problems, just reduce it to its simplest. You only ever want to look at one effect. So in this case, the O-methoxy is going to give me the largest lobe at the end, and the Z group is also going to give me the largest lobe at the end, so the prediction, and indeed the observation, is that you will get just that compound. Okay, so that's as far as I wanted to get today, so we'll stop.